Hello everyone. Today we're going to be doing a stoichiometry review, so just our last unit of study. If you remember from our moles unit, I'll just circle what we were doing. We were just dealing with this part of our flow chart. So we could go from volume, and we could go to moles of the same substance, and from moles we could go to particles of that same substance. So with stoichiometry, we're pretty much just doubling our last unit of study. So instead of dealing with the same substance the whole time, we can now go from volume to moles of that same substance. And then we can go from moles of one substance to moles of the next. And we can finally figure out, for example, the volume. We could figure out the mass of that new substance, or we could also figure out the number of particles of that new substance. So let me just erase my arrows that I drew. There we go. And we'll just take a couple of notes, and we'll dive into some examples. So it says that stoichiometry is the section of chemistry that involves using relationships between reactants and products in a given chemical reaction to determine the desired quantitative data. So in every question that you get, you will be asked to figure out something. Okay? It'll be specific on what you should be figuring out. And in a balanced reaction, we think of the coefficients as the amount of moles required of each substance. So let's get into our first example. We have the reaction phosphorus is reacting with oxygen gas to produce diphosphorus pentoxide. So the first thing we're going to do is we are just going to balance this reaction here really quick. So we're going to need 2 moles of diphosphorus pentoxide. We need 5 moles of oxygen gas, and we will need just 1 mole of phosphorus, and that 1:5:2 ratio should work here. So the question reads, if we had 0.64 moles of phosphorus and an unlimited supply of oxygen, how many moles of diphosphorus pentoxide would be produced? Okay, so we already know moles of phosphorus, and we are trying to figure out how many moles of diphosphorus pentoxide is produced. So I'm just going to scroll up to our flow chart really quick and draw out what we're going to do. So we know moles of one substance, and all we are doing is we are going to moles of the next. So we just have one conversion to do. So let's scroll back down after I'm done erasing here. We will begin. So we have our reaction balanced. We have a 1:5:2 ratio, and we're going to we're going to start out with what we know. So we know we have 0.64 moles of phosphorus, and we'll do our time sign line. And we want to end up with, I'll just draw an arrow, we want to end up with moles of diphosphorus pentoxide. So we are going to use the coefficients from our balanced equation in this step up here. So I'll just scroll up and show you. Whenever we are going from moles of A to moles of B, or moles of our original substance to moles of our wanted substance, we're going to use the coefficients from our balanced equation. So since we want to end up with, again, I'll draw an arrow, we want to end up with moles of P2O5, we're going to use 2 moles from our balanced formula on top. So moles of P2O5 on top. We're trying to get rid of moles of P4, okay, because we began with moles of phosphorus. So we'll be using 1 mole of P4 on the bottom. So write that down. Perfect. So if we type that into our calculator, all we will go is 0.64 moles multiplied by 2, and that should give us our answer. So if you do type that in, you should get an answer of, let's just see here, let me type it in, 0. I think, let's just take a look. Oh no, 1.28. So let's just write that down. 1.28 moles of P4. And in this unit, we are doing significant figures, so we will have to round up there to 1.3 moles of P4. And that should be our answer there. Sig figs are good. We just had one conversion to do, so that looks good to me. All right, let's scroll down to our next example. So in our first one, we just did one conversion from moles of A to moles of B, and this next one we'll do one more step, I believe. So it says, for the reaction between sodium hydroxide and sulfuric acid, if we have a mass of 5.6 grams of sodium hydroxide, how many moles of sulfuric acid would be needed? So again, the first step we're going to do here is just balance our equation up. So let's take a look at our possible coefficients here. So we should have, let's just take a look. Let's try 2 sodiums. We'll have 1 sodium there. 1 SO4, 1 SO4, and we have 2 hydrogen. I believe that should do it there. 2 oxygen. Yeah, that looks good to me. So 2, 1, 1, 2 for our balanced equation. And our next step, we're going to write out with, or we're going to start off with what we know. So we have a mass of 5.6 grams of sodium hydroxide. Okay, and we want to get 2 moles of sulfuric acid. Okay. So just quickly looking at our flow chart here, we're starting with mass of A. I'm just going to erase what I had before. So we're starting with mass of A, and we want to eventually end up with moles of B. So our first conversion will be 2 moles of A, and we'll have 1 more to moles of B. So let's take a look. So we'll start off with, again, 5.6 grams of sodium hydroxide, so NaOH, time sign line. Perfect. And we have to get 2 moles of NaOH. So we're going to need that molar mass there. I'll save you some time. I have it written down already. So I have 1 mole of NaOH on top, and that's over the molar mass, which is just 40.00 grams of NaOH. And we'll do one more conversion here because we want to eventually end up with, I'll just draw a little arrow, moles of H2SO4. So again, this is the step where we use our coefficients from our balanced equation. So we will go 1 mole of NaOH on top. Oh, no, my bad. 1 mole of H2SO4 on top. There we go. That makes more sense. And we are crossing off or getting rid of moles of NaOH. So again, from our balanced equation, we'll go 2 moles of NaOH. And that will get us to moles of H2SO4, which is our goal from this question. So if you do type that into your calculator, you should get an answer of, let's see if I have room here. That's a messy 0. Let me redraw it. 0.070 moles of H2SO4, and with sig figs that looks good. We were given 5.6, so we can only keep 2. This 7 and this last 0 will be significant, so our sig figs look good. Perfect. So that's our final answer. Next up, we get into limiting reagents, which, in my opinion, is the most difficult part of this unit. So it says, in a chemical reaction, there is sometimes going to be a limiting reagent. So this is when there is not enough of one reactant to fully react with the other. So some rules to follow here. Number one, we're just going to balance our reactions. So same thing we've been doing this whole time. We have to then choose a product to find the amount produced. So we're going to look at rules 3 and 4. It says determine the amount of your product made with one of the reactants. And then you will just redo that with the other reactant. So it says rule 4, determine the amount of your chosen product made with the other reactant. Finally, rule 5, it says the reactant that created less of your product will be your limiting reagent. Okay, so let's take a look at one example here. We have zinc, and it's reacting with hydrochloric acid, and it's going to make zinc chloride and just H2 gas, or hydrogen gas. Okay. So it says if we combine 3 grams of zinc with 3 grams of hydrochloric acid, what will be the LR, or limiting reagent? What volume of H2 will be made? And finally, how much excess will be left over? So this question, it does look for a specific product. It looks for H2. So that kind of takes care of our chosen product. I think we would like to find we'd like to choose H2 as our one product. So we already know that. But we also have to balance our reaction. So I think this is just going to be, let's take a look, 2 hydrogen over on our product side. 2Cl, 2Cl, 1 zinc, and 1 zinc. So just a 1, 2, 1, 1 ratio. So step 3, it says we're going to determine the amount of your product made with one of the reactants. So our first reactant, I'm going to use zinc. So we know we were given 3 grams of zinc, and we'll have to go to moles of zinc first. So that'll be just 1 mole of Zn over the molar mass. So the molar mass of pure zinc is just 65.39 grams of Zn. We'll have to do one more conversion because we have to figure out how much H2 is produced. So I'm just going to find moles of H2, and then with our LR, we can figure out the volume of H2 produced. So from our balanced equation, we will go to moles of H2. So again, we'll use that coefficient from our balanced equation, 1 mole of H2, and that's over 1 mole of zinc. So 1 mole of Zn, perfect. And if you type that into your calculator, you should get something around 0.4588 moles of H2. And since this is not our final answer yet, we don't have to worry about sig figs quite yet. We will get to that in a little bit though. So step 3 is done. We have determined the amount of product made with one of the reactants. I'll check off what we've done so far. So we've done 1, we've done 2, and we've also done 3. Step 4 says to determine the amount of your chosen product made with the other reactant. So we've done zinc. Now we must do our hydrochloric acid. So again, we begin with 3 grams of HCl. So same thing, we'll go from grams of HCl to moles of H2. So the step in between there, we'll have to go to moles of HCl. The molar mass of hydrochloric acid is 36.46 grams of HCl. And one more conversion here from our balanced equation, remember. Okay, so 1 mole of H2 on top, and this time I'll just draw a little arrow here. For every 2 moles of HCl used, there's only going to be 1 mole of H2 produced. So our ratio of 1/2 does make sense here. And if you type that into your calculator, you should get 0.04114. And let me just make sure that is correct here. I'm just going to type it in really quick on my calculator. So 3 grams divided by 36.46, and that is divided by 2. Yep, that makes sense. And I'll also type in the other one. So 3 grams of zinc divided by 65.39. And so I did mess up on the first one. I missed a 0 in the decimal spot. So let me just erase that quick. You should have actually got 0.04588 moles of H2. That makes more sense. There we go. So we have figured out moles of H2 produced with both of our reactants. And since this one is smaller, that means that 3 grams of HCl can produce less H2 than 3 grams of zinc can. So since 3 grams of HCl can produce less, it's going to be our limiting reagent. So now the next part of the question, it asks what volume of H2 will be made. So while we're doing that part, we need to use the amount of H2 produced with our LR. Okay, so we're going to go 0.04114 moles of H2 is produced from our LR. And we're just going to volume. So since it's volume of a gas, we can use that gas constant that we learned in our moles unit. So it'll be 0.04114 moles of H2 multiplied by 22.4 liters of H2 for every mole of H2. So our units still do cross off here. Oops, I erased that. So moles of H2, there we go. So our units still do cross off. And if you type that into your calculator with sig figs, you should get something around 0.92 liters of H2. Okay, and again, that makes sense with our sig figs. We were given 2 in our question for both of our numbers given, so 3.0 grams and 3.0 grams. So our sig figs do make sense. And finally, one more step to this. It says how much excess will be left over. So we know our LR is 3 grams of HCl. So that means 3 grams of zinc will be in excess. Okay, so zinc will be in excess. We have to figure out how much of it is left. Okay, so how we can do that? We can go from grams of HCl to grams of zinc, and what that's going to give us is the mass of zinc used in this reaction. So if we know the amount of zinc used, we can simply subtract that from our original amount of zinc, which will give us our excess. Okay, so let me just make a quick space here. I'm running out of room. There we go. Maybe one more. There, that's better. So let's begin. We have 3 grams of HCl. So our original amount of HCl, and we're going to eventually end up at grams of zinc. So we have a few steps on the way. That is over 1 mole of HCl, and our molar mass on the bottom, so 36.46 grams of HCl. So now we're on at that mole to mole conversion. So that's going to be from our balanced equation, remember? So we'll just scroll up and take a look. So we are going to moles of zinc here. So we'll use that 1 from our balanced equation on top. So 1 mole of Zn on top, and I believe it was a 2 for the HCl. It was. So 2 moles of HCl on the bottom because we're getting rid of moles of HCl. Perfect. And we just have one more step, which involves the molar mass of zinc, which we have 65.39 grams of zinc, and that's just over 1 mole of Zn. Okay, so again, that is going to get us the amount of zinc used in this reaction. And I'm just going to make one more little space. Perfect. So if you type that into your calculator, let's see what we get. You should get 2.69 grams of Zn used. Okay, so this is how much zinc was used in this reaction. Now we can just subtract that from our original amount. So we have 3 grams of zinc, and that is subtract 2.69 grams of zinc. I'm just going to erase that and put zinc in. There we go. And if you take a look at that, if you type that into your calculator, you should get 0.31 grams of zinc is in excess. Okay. So I know that's quite a long example, but those are your steps to find your LR, your wanted quantitative data, and then also your excess. Okay. We just have one more little portion here in this video, that's percentage yield. So when performing calculations using stoichiometry, the mass found is called the theoretical yield. So what we found while doing all of these questions is the maximum amount of product that can be produced from these reactions. Okay. So when completing a lab in real life, chemists or scientists or students, they don't always get the maximum amount of product possible. So this is called the actual yield. So theoretical is found using stoichiometry and calculations, while actual yield is found doing the lab or performing the lab in real life. Okay, so a very easy or a simple formula that we can use is our percentage yield will be equal to our actual yield over our theoretical yield multiplied by 100%. Okay, so let's do a quick example and we will be all done. So it says the limiting reagent in the following reaction is 1.56 grams of barium chloride. So while completing the lab, we isolate 1.64 grams of AgCl, which is our wanted product. It asks, what is the percentage yield? Okay, so first off, we have to write down our balanced formula. So we have barium chloride and it's reacting with silver nitrate, so AgNO3, and that is going to produce our wanted product, which is silver chloride, and another product, which is just barium nitrate. Okay, so BaNO3 bracket 2. So we have our formula. Let's just balance it quick. It should be a 1:2:1 ratio here. So we're all balanced, and we already know our LR from the question, which is really nice. We know that it's 1.56 grams of BaCl2, so I'll square that off so I know for future reference. And it also says we isolate 1.64 grams of AgCl, which is our wanted product. So I think we should write down a couple of things there. So 1.64 grams of AgCl, that's going to be our actual yield. So I'm going to write that down quick. That is what was found while doing the lab in real life. Okay. And we can start our calculations with our LR, which is 1.56 grams of BaCl2. So 1.56 grams of BaCl2. And if you read the question again, we know where we want to go here. It's asking us to find the percentage yield, and it also gives us our wanted product, which again is AgCl. So we should be going from grams of BaCl2 to grams of AgCl to find our theoretical yield. Okay. So 1.56 grams of BaCl2 times sign line. We want to get it to moles of BaCl2 first. So 1 mole of BaCl2. And that is over our molar mass, which is 208.23 grams of BaCl2. Our first units are crossed off. Now we want to get to moles of AgCl because we eventually want to find the mass of it. So from our balanced formula, or our balanced reaction, we have 2 moles of AgCl for every 1 mole of BaCl2. So we have to take that into consideration. And if we were to stop there, we would be at moles of AgCl, but we want to get to mass. So we have one more step here. We'll multiply this by the molar mass of AgCl. So the molar mass is 143.32 grams of AgCl. Sorry, I'm running out of room. And that is over 1 mole of AgCl. So if you type that all into your calculator, folks, you should get something like 2.147 grams of AgCl, so 2.15 grams of AgCl. However, this is not our final answer yet because it's asking for percentage yield. Okay, so we'll use this. 2.15 grams is our theoretical yield, and we also have from our question 1.64 grams as our actual. So 1.64 grams is our actual yield. So we can use that formula that we looked at before. So actual over theoretical multiplied by 100% to give us our percentage yield. So we found our theoretical yield. So this was found through Stoich, and this is our max amount of product from this reaction. So that is as much as is possible. And from our lab, we got 1.64 grams. I'll just erase that really quick. So this was found in real life. So found in real life. So if we want to find the percentage yield, I'm just going to write the formula again for that. So the percentage yield again is just the actual yield, and that's over the theoretical yield. So remember that your smaller number is always going to go on top and your larger number is always going to go on the bottom. Just as a little tip. And that's multiplied by 100%. So we just have to fill in our variables here. Our actual was 1.64 grams of AgCl, And our theoretical, what we figured out through stoichiometry was 2.15. So 2.15 grams of AgCl, and that's just going to be multiplied by 100%. And if you type that into your calculator while taking sig figs into account, you should get a percentage yield of 76.3%. Okay, so 76.3% will be your percentage yield for this question. I hope this review on stoichiometry helped. Thanks for watching.